to the another video program about the RStudio, and today I'm going to discuss about how you can perform a linear regression model in the RStudio. Let us start with the basic introduction about the linear regression. What do you mean by linear regression? Linear regression is a kind of mathematical model in the econometrics which determine the mathematical relationship between the regressor and regressant, that is a dependent variable and independent variable. Through this linear regression model, we can establish a mathematical and quantitative equations that can explain the independent variable can be explained by the dependent variables. You can see here it is the simple linear regression model equations with the one variables. Here y is the independent variables, or the variables that we are trying to explain, or we are trying to determine the value, and we don't know the exact value of that. Later we will use this model to predict the y based on the explanatory variables, even though we do not know about the y. And beta 1 and beta 2 are the coefficient. Beta 1 is the intercept basically, and beta 2 is the coefficient of the x variables. We can have the multiple linear regression model having the more than one dependent variables, but for today we will discuss just one dependent and one independent variable. And here E or epsilon sometimes describe about the error term or the white noise effect. It means when we are taking or we are just considering x to determine y, there might be the other variables which have effect on the y. So whatever left or whatever other variables that can affect on the y can be summarized by the, or can be captured by the, will be captured by the E, that is error terms. This is the very basic definition or the basic explanation about what is linear regressions. Let us start how we can proceed. To import the data, you can import the data set from here, from any data set, maybe stored in the Excel form or the SPS, SAS, Stata, whatever. You can just click here. For example, I have the Excel file, and you can go to the file where you have the file. Then you can just choose the file and open it. But the alternative way, let's say, let me see. The alternative way is we can directly give command to import data from the from your computer to the RStudio. Let's run the library read actual package. Then I will run the language, that is I'm going to import the tomato price as a read underscore actual, and I have the data in this folder, download folders. This is the folder directory. You have to find out the folder directory. Then the file name is tomatoprice.actual. Then it will import the data file to my computer RStudio. Here, one thing you have to consider, or for your convenience, here I have imported the data file as the name of the tomato price. But tomato price is little bit lengthier, so you can make it a shorter form, whatever you like. So for my convenience, just I write the price, because we are just dealing with the one commodity, and we are going to predict the price, future price, using the price data, whatever we have. Later we will see what kind of data we have. First, just see. I will change the price. The data set name is the price from the tomato price. Now you can see here, it is just, I have changed the name, I haven't done anything. I just imported data, then I just changed the name of the data frame. Let's say the structure of the data, what kind of a structure it is. So for this structure, we just write str of str command, and let's run this as the structure price. Then you can see the result here. We have price from price of the 1,141 observations. We have the date, we have the minimum price, we have maximum price, we have the average price, and we have serial numbers. Okay, this is just the structure, and all are in the numeric variables except data format. Okay, so let's summarize our data set. All the data, let's run it. As the summary price is the summarization function in the R. So here you can see the summary function. We have the date, minimum price, maximum price, average, and serial numbers. From the date, the minimum price is 2017 101. That's the we have the data from the 2017 January 1st to the maximum data you can see here. That's 2020 to 15. So we have the data from 2017 January 1st to the 2020 February 15. For the minimum price, we have the minimum price is 20 rupees per kg, and the maximum price is 150 rupees per kg. That's only for the minimum price. And you can see the first quarter, median, mean, third quarter, like that for the every variable, the minimum price, maximum price, average. And the serial number is just a number. It starts from the 1 to the 1,141 observations. Okay, before proceeding any regression models, we need to think about what kind of data is it, whether they have the sufficiently satisfied our linear regression assumptions. So we can analyze these data from the graphical analysis. For this purpose, in the linear regression models, we use basically scatter plot, box plot, density plot, and also we can use the histogram to see the distribution of the data. Okay, let's start with the scatter plot. For the scatter plot, command is scatter.smooth. For the x-axis, we have chosen minimum price, and for the y-axis, we have chosen maximum price. And x lab is the label for the x-axis, y lab is the label for the y-axis, and the main is the minimum maximum price is just a heading or the main title of the graph. If I choose it all and run it, then I will get the figure here. They are quite in the linear pattern. You can see it's quite linear. So minimum price and maximum price are highly correlated. You can see from the graph here. Another, let's see how the minimum price of the particular date is related to the minimum price of the previous day. For that, we put the same command, that is scatter.smooth, and x variables price of the price for the maximum, and for the another y variables we take a log of sorry, it's a lag of, give me pardon, it's the lag of the price of minimum, that's a backdate of the minimum price. So it's just the lag of minimum price. Then let me run it. Just run it here. You can see they are quite condensed, and they are in a linear pattern, except for the later part. For the higher price range, there is some it looks there is some kind of the outliers, but up to 100 the rupees to 2200, they are quite condensed and they are highly correlated. Okay, in this way, we can see the relationship between the variables. Let's start with the box plot. Box plot gives you the idea about the outlier. Here, the command for the box plot is just simple the box plot, and in the parentheses you just write the name of the interest variable. In our case, there's a minimum price from the price data set, and the minimum. The main is the title. There's the minimum price of the, let's say, minimum price of tomato. Then in the subheading, we just paste the outlier box, and box plot statistics. There's a price of for which outlier. It means the price of the minimum outliers, and inside outlier we just pick the value of outliers. It's just a command, and let me run this command. You can see here is around above the 100 rupees. There are the three observations which are outliers. You can see the outlier here above the 100. There are the three variables, but they overlap here, so it's not clearly seen as viewable here. Let's just plot the box plot for the maximum price. You can see here above maybe 150, but there are the 4 outliers. In this way, you can just see, you can visualize how many data set are outliers, whether you have to take any corrective action for the outliers or any such remedial actions. Also, by the histogram, you can see the distribution patterns. Here you can see maximum distribution, maximum values range from the 20 rupees to the 50 rupees. But there is also the significant observations up to 100 rupees, but beyond 100 there are very few observations. Even in the previous graph, we have seen very few observations beyond the 100 rupees. For example, if you take take a look here, there are 3 observations beyond 100 rupees. So it gives the idea about your data. It can help to visualize your data. How fine is the data, and how it fits in the linear regression model. Let's see the one command here. I took that, whether it's just a logical command that says if you have the more than 100 rupees as observations, then it will get the print true. You can see here is one true, otherwise all are false value. That means except 3 variables, as we already discussed earlier, all are under the 100 rupees price range. So it's a histogram for the maximum price. Just I run it. I have already discussed about it, just to see the variables. After the 100, maybe 105, there is data, significant data. Otherwise, there is some outliers. Is is negatively truncated or negatively skewed data. Regarding the density plot, it also gives the nice visualization of the density plot. And there is the simple command is the plot, and the function is density, and our interest variable is the price, and the maximum price. Under the price data set, there is a maximum price. We just write the name of the graph. That is the minimum. Sorry, let me correct here. It's the maximum price. Maximum price of tomato. Let me write here. Tomato. And y label is frequency, and in the subheading we are trying to print skewness, and we will get a round figure. That's round mean the command for the round figures, and we will take the package. That is the package you have to install before using it. E1071 is the package, and we will give double semicolon to access the function, and inside the package E1071 there is a function skewness, and we'll take the skewness um, of the minimum. Okay, let me here we are just using the maximum. Let me correct here the maximum, and the rounding will be done in the two figures. Okay, and here you can see later after plotting we will add the polygon, and in the polygon for the density, as we have already mentioned there, of the, let me correct here the maximum value, because let me make a consistent throughout the process, otherwise it will mislead us or it will be the mistake. Okay, let me plot this function first. You will see the function here, a graph. It's just very sketch. So to make it fancy, we will give the another function as a polygon function for the density for the same picture, and the color will be printed as red. You can see here the color red. Let me print it here. See, it looks nice. How our price data is distributed, you can see here. It is it is not exactly the normal distributions, but for our this practice, it's okay. After visualizing our data set, or after analyzing the visual analysis of the data set, we have to proceed about the correlation analysis. The correlation is the statistical relationship between the two variables, whether they are positively correlated or negatively correlated, or what's the magnitude of correlation. For the magnitude, it ranges from the -1 to the +1. If there is a -1 correlation coefficient, it means the two variables, two interest variables, is perfectly negatively correlated. And if the correlation coefficient is +1, it means it has the perfect positive correlations. But one important thing I have to highlight here, correlation and causation, or the causality. Correlation and causation are entirely different things, but most of the case we often get confused, or we do not consider about that. For doing the regression analysis, for performing the regression analysis, we just carry out a correlation analysis, but we do not care about the causation analysis. But indeed, causation is the very basic things we have to think about. To make it clear, as I mentioned before, correlation is a statistical relationship between the two given variables. But causation is whether there is a causal relation or not. Take an example. If you take the data of rainfall and sales of umbrella, and if you perform the regressions, that might produce perfect correlations, or the higher level of the correlation, positive correlations, because during the rainy seasons, sales of umbrella naturally increase. Then you can conclude that there is a positive correlations between the umbrella sales of umbrella and the rainy seasons. Or you also can get the other way result. I mean, there might be the negative correlationship that during the rainy seasons, the correlation coefficient may produce the negative correlation coefficient. Then you will interpret the result as there is the negative correlations between the sales of umbrella and the rainy seasons. It means there is no good or no encouraging sales of umbrella during the rainy seasons. Later, if you know about the data set, if the provider of the data set said, oh, it's my mistake, it's my fault that I provided you the sales data of umbrella of city 1 or country 1, then I provided you the rainfall data of the another cities. For example, the rainfall data is of United States, and the sales of umbrella data of the Russia or the China. Then how you can interpret this correlation coefficient? If you fit if you fit in the any statistical package, it will produce some kind of the result, whether it's positive, whether it's negative, whether it's the small magnitude, whether it's the larger magnitude. It doesn't matter. Before that, we should be aware of the causations. It is very sure that rainfall in the United States might not directly correlated with the sales of umbrella in the China. Though today we have the globalization, there might be the relations, but at the localized level, local sale, there might be the relationship between the export of umbrella. If the yeah, China is the exporter of the major exporter of the umbrella, but otherwise it will not be the case. Therefore, we should be clear of the correlation and causations. Okay, let's take the test of minimum price and correlation between the maximum price. What will be the result? There is not very higher level of the correlation between the minimum price and the maximum price. In the same way, we can put the correlation test for price of minimum and price of average value. There is a higher level of correlations, and correlations between the price of, just for example, of the minimum and the lag value of price, minimum price, let's say. So it's not correlate because we have the one missing value. If we take the lag value, it will be the minimum price. So okay, we will not check this right now. Okay, in this way you can see there are the higher level of the correlations. Next, the next round is building models. Then we have to build a models. Let's develop a model for the test of the minimum price. So I give the model name as model 1, just it is a name. You can write anything. Then we will assign this model, and for the command of the linear models, it is lm. It's just simple lm. Then we will run the minimum price, and just for the first case, we'll just add the serial number because we are just taking its own value, just how it is proceeding. Just we are producing a trend, and the price data is the price. Okay, let me run this model. Okay, this is the model 1. It is run successfully. Then we will take the summary of the model. You can see here for the first, it is start from here. This is our formula. Minimum price and the serial number. We are just producing a trend. So residuals, here is the minimum residuals is -30, and first quarter is -2, median is -4, third quarter is 79, and the maximum is 91. So if you take a look about the intercept, we have the intercept value. This is a beta 1, it's 35.68, and the associated standard error is 1.0, t value is 35, and p value is 2 to the power of -16. And if you see the here significance level, it is highly significant. And for the serial number, it is the coefficient beta 2 coefficient is 0.02, and corresponding standard errors. Standard error t values and p values are there. You can see the significant core. What's the symbol of that asterisk? For the, if they are highly significant at 0, then it will produce a triple star, 3 stars. If it is significant at 0.001, then it will produce 2 stars. If it's significant at 0.01, then it produces 1 stars. And if it is significant at 0.05, it produces dot, period. And if it is significant at 0.1, then it will produce nothing. So here is R square. R square is pretty low, just 0.15. It is just 15% variation is given by the just trend, the simple but trend. So it's not very good model to adopt it. You can see the F statistics and degree of freedom here. Then after developing a model, then we have to check the p-values. It is highly significant. We check the R square and adjusted R square. Here is a very there is difference between R square and adjusted R square, but we often miss the adjusted R square. We just consider the R square. Actually, R square is the capacity or the percentage that the explanatory variable is explaining about the independent variables. But adjusted R square is the value. If you take unnecessary variables in the model, it will penalize you. So it adjusted the R square value. That's why we have to consider the R square. In this example, it's just a single variable, single explanatory variables. That's why it's almost the same. Okay, let's develop other computative models. The model one is just one model. Let's develop the another models, and let's check the whole things again. For the model 2 is the linear model LM. Then we will regress a minimum price of the tomato to the lag value of its price. It means 1 day back's value, the value of 1 back. Then the price data, we are taking the data from the price data. Let's run this model. Okay, let's check the summary of the model. Okay, here you go. The minimum residue is -49 and the maximum residue is +45. And if you take a look about the beta coefficient, that is intercept coefficient is 2.62, and and the coefficient of its lag value, or the x, is 0.94, and both are highly significant. Let's see. The standard residual error is 6.035, and the degree of freedom is 1138, and one observation is deleted due to the machine. Here is you can see the notice what it has done, because while taking the lag value, there should be the one value deleted, because in the one lag we will miss the one value. If you see the multiple R square, it's quite increasing. It is quite encouraging as compared to the previous model. Previously it was just 0.15, but now it's 0.8961. It's almost 90% of the R square, and as the R square is the same. So as compared to the previous model, model 1, model 2 is far better, but we will see later how we can choose the better model. Let's run the another model, another competing model. That's the model 3. It's LM, minimum of the lag, and the maximum minimum. We will regress the minimum price to the lag of the maximum. How the previous maximum price will affect the minimum price of particular day, or the present day. Let me run this model, and let me see. Sorry. Let me see the summary. Here is the summary. Okay, the explanation is almost same. If you see, the error is a little bit higher at the minimum side, -52, but maximum error is almost same. Coefficient is intercepted -1.59, and the lag value is 0.92, and both are significant. Then coming to the R square is the same. R square is almost same. A little bit lower, but almost same. So after coming this, how we can decide which model is better? The one criteria is AIC and BIC criteria. It's almost same to to rank the model, which model is better. For the we will take a look of the AIC. For the we just write the AIC and write the name of the models. We have the 3 models. We don't have fourth model at this moment, so we have just 3 models and just run it. Then it will produce the AIC coefficient. Okay, see, there are the value of AIC and model to produce. See, the model to produce the minimum values as compared to other models. So from the AIC rule, we will take the models having the lowest AIC. In our case, model 2 is the better model. Okay, which model is best? We have chosen the model from the AIC criteria. You can also do the BIC criteria. Now, before using the prediction function, how to predict it, we have to use we have to do some kind of the exercise here. Okay, for the predicting, we need to develop a training model, which will develop a model. Then we will test this model in the testing data set to make the model, to assess whether our model satisfactorily predict the other in other case. So for the training data, we are just making a set. That is, we will take the first 1,000 observation as a training data to build a model. It's just a training. I have given the name. Then from the price data set, we will take the first 1,000 observations. I will run it. Then let's see the summary. Fine. See, we have the all variable. We have all variables of the past 1,000 data set from the price data set. For the testing data, we will take the data set on what the testing training data. So that is starting from the 1,001 to 1,141 data set. Okay, this is our testing data set. Let's see the how the different data set is created. Our original data set has observation, and row means the number of the rows. That's the number of observations. That is, we have 1,141 observations. For the training data set, we have 1,000 observations, and the testing data set, we have 141 data set. It's a pretty good number of the observations. So first, we will develop a model based on the training data set. As we have developed the previous model, we will develop the LM mode. LM mode, it's just name. Then we will assign it as the LM, linear model function. Then we will regress minimum price against log value of maximum price. We are trying to see how the previous maximum price will affect the next day minimum price. Then we are taking the data, we are taking the data from the training data set. We are not taking the data from the original price data set. So it's very important to consider. Let's run it. Okay, our model is fine. Then we will test the model in the, before doing that, let's see the summary of the model, how we get the I will get the results. There's the LM mode. Okay, LM mode. Let's run it. See, model is very fine. It has 96% R square, even better than the previous one. R square residuals is quite small than even the previous one. So it looks very good from the model point of view. Now we have to predict the values using this model and using the testing data, not in the training data. So we will run it. This is the name, minimum price predicted values, and just we want to predict the value from the linear model, the model we have just developed, and using the testing data. Okay, let me run this code. So it's fine. So let's see, we have already take a look of the summary of the model. Then we will create the a data set from the predicted and the actual data set. For its actual predict data set, I have just put the name, that's actual, and the predicted data set. And we will make a data set as a data frame, that's data frame. Then we will bind, we are going to bind two values by the column. We will bind two data frame into the one data frames by column, that is C bind. The actual data is testing data, because we have already developed the testing data of the first 1,000 observations. Minimum price of the testing data, that is the actual values. The actual values that we have assigned, and the predicted values is equals minimum price of the predicted value. Is we have created that variable here. Okay, let's run this command. We have this very good one. Okay, let's run the correlation coefficient. That is how well it is fitted one. So if you run it, then test the correlation coefficient. Oh, it's fine. It's 95% correlation. It's a very good correlation. It's very good predictions. If we take the correlation in the matrix form, it's the same way. If we take the head minimums, mean what's the variables, we have the actual value 60 and predicted 66, 65, 66, 65, 66, 55, 58. This is just first value. So how you can make the minimum maximum criteria? Minimum maximum criteria, we have the value here, and if we run the minimum maximum accuracies, our model is 92% accurate. Otherwise, we have another values, that is mean absolute percentage error. If we take the mean absolute percentage error, it is 0.087. Error is pretty low. But we can't using the alternate way, using the package DMWR, we can just run it to get all values at once.